All right, so good morning, everyone. Let us start today by first talking about the book of the day. So it's called Contact Mechanics, as you can see here, and it's written by Johnson. So it's a very important book dealing with the contact of two elastic objects that can, in addition, be adhesive. So you have like van der Waals forces and so on. And so it's a framework that is either useful for, hard materials in a sense in industry, but at the same time, you can go to very soft materials and even biological objects at the end. So for instance, you all know about the Hertz contact when you push an elastic sphere onto a substrate, and what is the relation between the force and the deformation of the object. It's not a linear spring. There is an exponent 3/2 due to the spherical geometry. But then you can refine this by adding some adhesion and even surface tension for very soft gels. And so this book is a very important one if you are dealing with such contact problems. Okay, so that is for the book of today. And so in terms of topic today, we would like to deal with DNA. And in particular, there was a very famous paper in the 70s that you can see here, or even at the end of the 60s, by Manning, where basically the idea is that he studies DNA-like molecule theoretically. He remembers that this molecule is charged, and the fact that you have charges around the molecule means that there are counter ions around for neutrality of the ensemble, and those counter ions, they are attracted to the charges. So you have a kind of decoration of DNA or any polyelectrolyte by counter ions. And this is very important because DNA is pretty linear as an object. And when you have this 1D-like geometry, you can show, and we will do that today, that there is a dramatic condensation of the counter ions. They are all attracted from far away and just will basically condensate, pretty much like a liquid will condensate from a vapor on a mirror, if you think about your bathroom. But here the charges will condensate on DNA, and so you will have a kind of a condensed state, liquid or solid, of counter ions on DNA. Therefore, viewed from far away, now this object is neutral, or at least the charge has been reduced by this mechanism. So it's a very important mechanism because it means that despite the fact that you have plenty of phosphate groups that are charged on a DNA molecule, in fact, the charge is reduced. And so the properties are very important, like the charge is central in biology. And so the properties of DNA in a cell will be completely modified by this mechanism. So it's a very important finding that we would like to discuss today. So in the Dropbox, you've seen this article. You can have a look at it. Basically, you will see after the tutorial, you will understand that we basically followed the main steps described here. Okay, that's the idea. So it's really following that. And of course, I've transformed that into a much simpler form, so with the key questions only. And so please take the tutorial number 7 so that we can start. All right, so now, let me share the whiteboard. All right. And we'll keep only this one on the side. Well, even not, you don't need me. All right. Okay, and just before starting, there was a question last time. Remember, we were dealing with the structure factor for a polymer chain in particular. And there was a question about, is the structure factor Gaussian? And rapidly, we discussed that, and it is somehow Gaussian because it starts from a summation of plenty of Gaussians, as we discussed last time. In fact, if you do that, you have the formula that we provided at the end of the tutorial, which is not exactly a Gaussian. You have an exponential minus something to the square, but you also have some polynomial and rational prefactors in front if you look at the exact formula. So the exact formula actually is in the tutorial. Okay, so it's not exactly a Gaussian. All right, so let us start with the topic of today. So we are considering DNA. So DNA, I could really say it's a kind of a polymer. Also, the main difference with what we did so far is that this polymer has some negative charges around on it. So they come from the phosphate groups typically, and they are very important because first, it means that the interaction between the monomers will be different. Now you have equally charged objects, so there will be a stronger repulsion, and so DNA will be more rigid. It will be more stiff than the ideal chains we described so far. And secondly, it means that there will be some counter ions in the solution. For instance, in the cell, in the water, you will have plenty of ions that will accumulate around the chain, and as I explained, perhaps even condensate on it. Okay, so the picture starts to be more complex than the one we described so far. So we will consider this system in a solvent at temperature T, and then we will add plenty of chains, and we will discuss the osmotic pressure and so on. So first of all, I would like to give you a flavor of the condensation mechanism proposed by Manning. So here is the idea. So let us start. So the idea is to describe the polymer chain as an infinite cylinder or an infinite line even, where you have equally charged points like that, and they are equally spaced with a certain distance small b of nanometric range. And also it's really an infinite description. So it's really a 1D line that goes from minus infinity to plus infinity. Okay, very simplified model for DNA. The rigidity of that object is really coming from the fact that you have a larger persistence length than non-charged polymers. Okay, so is it valid? Well, the question is that, again, reality is more like that. Okay, and therefore you have typical sizes of loops that are provided by the persistence length, which is the length needed to forget your initial orientation, typically. And at the same time, we are saying that, well, we have monomers. I won't draw all of them, but they are spaced by a certain distance, small b. And so the first requirement for this model to be valid, well, you need to have b much smaller than the persistence length. That's a prerequisite. So that really you don't see the curvature, and you can stay very linear and stiff. The second aspect is that I told you that you are putting charges, meaning that there are also counter charges in the solvent, and therefore you want to make sure that you don't have non-local effects. For instance, here when I draw this line, basically this guy will don't speak to that guy. There is no interaction between the two. They are too far away in a sense. So we want to avoid interactions between, let's say here, those guys. We would like to make sure that there is no interaction like that. And so the interaction, the Coulombian interaction between charges is generally screened by the counter ions, and you have around a certain ion, a certain charge, you have counter ions around, and so you have a kind of cancelling of the Coulomb interaction over a distance that is the Debye length. Okay, so beyond that distance, well, it's completely neutral, and you can neglect the Coulombian interaction. And within this distance, in contrast, you have the Coulombian interaction. So you want also this Debye length to be typically much smaller than LP, so that you don't branch some non-local interaction in your 1D description. Okay, so those are the two prerequisites so that we can really describe DNA this way. And we will do a further step. We will assume that we look at the system slightly far away from the axis, which means that in fact we can consider it as a uniformly charged infinite line, and with a linear charge density, which is E over B. Okay, so we replace really the points by a uniform distribution. That is the model we want to study, and we would like to calculate the potential, the electric field, the interaction energy with counter ions, and look at the distribution of counter ions associated to that energy or interaction. And we would like to show or evaluate a criterion for condensation or not. Okay, that's the idea. So let us start now. So first, we would like to calculate the electric field and the potential. So we would start by the electric field by using the Gauss theorem here. And basically what we can do is to say, well, first we can evaluate the symmetries of that problem. So again, the lineic, I can write it this way, density of charges is E over B. And so what are the symmetries? I'm interested in calculating the field at a certain distance d from the, let's say, z-axis here. Okay, and the symmetries, what do you think about the field? How should it be oriented? So do you think the field that we are dealing with is a priori a function of, let me write it this way. It's an amplitude. Oh no, let's skip that. It depends on the distance, the angle if I now rotate around that axis, and also a priori z. So what do you think first about the dependencies on all those parameters? Do you think that there is, yes?
Theta does not appear because we have invariance by rotation.
Yes, it's clearly a problem that is invariant by rotation, okay? So there is no particular angle, okay? What else?
We have an infinite line also.
Yeah. All right, so a priori, the field does depend only on the distance to the axis, okay? And what about the orientation of that field? So again, the symmetries. So remember, if there is a plane of symmetry for the charge distribution, since the electric field is a real vector, then it must be contained in that plane. So now I'm considering the electric field at that position, D. So how is it oriented? I mean, look at all the symmetries. You can take a plane, for instance, that is the plane of the whiteboard here, containing the red point. Well, it's clearly a symmetry plane for the system, okay, because it contains the full line and the point I'm considering. So the field must be in the whiteboard plane first. But at the same time, I could also take a perpendicular plane that is perpendicular to the z-axis and containing the red point. And again, this plane is a symmetry axis because we have an infinite cylinder, so both sides are totally mirror of each other, and they contain and this field contains the red point. So it's also a plane that should contain the field. So the intersection between the whiteboard and the perpendicular plane, well, it means that it's necessarily something which is along the radial direction. So here it's d because the distance has been called d, but it's really the vector here along the radial direction. Okay. Okay, so it's simplified, and so now we can basically take any point here and create a kind of cylinder here around that point, and this cylinder we will take it with a certain distance, which is b, so that we have really, remember this quantity, we have really one charge inside. All right, so let us apply the Gauss theorem. So if I integrate the field over the surface of that green cylinder, and let's assume I'm taking a closed integral. So I also consider the border on the side, but those side fields, they won't contribute because ds is like that outside, and the field is radial, so it's orthogonal, the product, so it will give 0. So basically, this will be E of d. Then the surface of the outer cylinder is 2 pi b times d. And from the Gauss theorem, this should be equal to the total charge inside divided by epsilon, the permittivity of the medium. So the total charge, well, since I decided to take B as the length scale horizontally, I have only one charge inside, and this should be divided by epsilon. Okay, so it allows me immediately to extract the field, which is E over 2 pi epsilon BD. All right. And since I'm interested in the energy of interactions with counter ions later on, it would be better to have the potential. So we know that, well, E is equal in statics to minus the gradient of the potential. And so it means here that it is minus the derivative with respect to D, sorry for the notation, of phi, which is only a function of D. Okay. So here I can say that phi is the integral of that quantity here. So I have with a minus, you have a log and any constant you want here, so that the log can be made dimensionless if you want. Okay, so that is the main source of the condensation mechanism or the divergence here, because you have a logarithmic field, which is very singular. And it's really related to this 1D geometry, okay? So we've exhibited that potential, and we would like now to transform it into an interaction energy for counter ions. So the counter ions, they are really placed everywhere around. And you have plenty of them here around the axis. And the question is, what is the interaction energy of one counter ion of charge? So let me just see where we are. We are at question number 3. And it's a counter ion with charge minus E, okay? So the interaction energy between the field created by the polyelectrolyte, this infinite line, and the counter ion is simply minus E times phi. And so since we had this formula, it's E squared over 2 pi epsilon B log of D, and plus any constant we want again, or minus EA. All right? So that's the interaction energy between the field and the counter ion. So we have the interaction energy, so now we can think about the concentration profile or the distribution in space of the counter ion. So what should we do now, according to you? Remember, we are in a canonical ensemble. We have a solvent with temperature T around. That is a reservoir. So how does the concentration of counter ions depends on the distance? No one? All right, so we will assume a Boltzmann distribution. Okay, we have an energy of interaction that depends on the distance. So we can say that the concentration of any species of counter ion will be provided by any reference, and then exponential minus beta u. Okay, so this means here the reference times, here we have E squared 2 pi epsilon over kBt, and then we have, which I can put inside the constant by introducing a renormalized constant. All right, so this is how the concentration of counter ions depends on the distance to the axis. Okay, so we can now work a bit on this, this quantity. First of all, I can notice that this could be rewritten the following way: 2 E squared over 4 pi epsilon kb t times 1 over b times log d. If I keep it here. And so here we recognize something that you might already know, which is what? What is the unit of that object first? What is the dimension? All right, you seem a bit sleepy today, right? So it's a length. We have a length here. So this is a length necessarily. And what length is it? Well, it's called the Bjerrum length. And this is the length you would get if you try to identify Coulomb's energy of interaction. Let me put this length here, and kBt. So it's the length, okay, beyond which Coulombian interaction dominates, and above which kBt dominates. So it's really the first length you can construct when you want to combine electrostatics and stat phase and thermal fluctuation. Okay, this is the first one you can do. So it's typically in the nanometric range for most ionic, or at least water and charges. And it means here for my study that I can recast things this way. It's a ratio of two length scales that are important in the problem, the Bjerrum length and the distance between charges on DNA. Okay. So I can now introduce a quantity that I call psi. That will be the control parameter of my problem, the ratio of those two only important length scales. And therefore, I can say that the concentration profile at a certain distance d, apart from a constant prefactor, is exponential minus 2 psi log of the distance, which is equivalent in saying that, well, it's the distance to the power minus 2 psi. It's a power law. You don't have any exponential anymore. It's the combination of that logarithmic potential and the exponential Boltzmann factor. So it's interesting. You have a decay of the concentration profile that is a power law from the axis. So you have the axis of your DNA with plenty of charges around, and then the concentration diminishes as you go away from the axis. But now that exponent is very central. Depending on the value of this, and thus the value of that ratio, well, you might have some very sharp behavior, because if this is, let's say, 1 over d, for instance, you will have a problem when you will integrate that, okay? This might lead to divergences, and thus the number of objects might diverge. This is the essence of condensation. So let us now try to identify the limiting exponent there. So we go to question number 4 now. Again, this is DNA, and we would like to evaluate. Let's take one charge, and we take a box around that charge that has a certain, so it's a cylindrical box. It has a certain radius d max, and it has a length which is b. So again, you have another charge e here, another charge e, and so on. The question I would like to ask is, what is the number of counterions? In this box. Okay, so the number of counterions per charge on DNA is equal to, well, the integral of the concentration profile over the volume of that box. Right? And so if now I put the proper dependencies, you have an angle, you have a dz between, let's say, 0 and b, 0 and 2 pi, and then you have the integral over the radius between 0 and d max, this guy, and then remember, and the concentration profile is written, so I put everything with the variable of integration r, it's the same. And so I get 2 pi for the first integral, B for the second integral. And then for the third one, I'm left with calculating this quantity, d max, dr, and then I have r to the power 1 minus 2 xi. Okay? So, which means that the total number is, let me just write it at the beginning of this blackboard. All right, so it's a polynomial function. So I can just take r to the 2, 1 minus xi, divided by 2, 1 minus xi. This is the primitive between 0 and d max. So any comment here on that number? First, do you see a particular value of xi emerging?
When xi equal 1, we've got a problem.
Yes, we see that when xi goes to 1, there is a transition between two regimes. That is correct. And the second point was? What else? Look at this bond in particular. This is a finite bond, so we don't care about the divergence at very large distances because we won't integrate towards infinity. However, this is annoying for certain values of xi. Which ones?
Xi less than 1.
For xi less than 1, it's actually good.
No, yeah.
The opposite, yes. For xi bigger than 1, the exponent over r becomes negative. So you have 1 over something, which is vanishingly small. So it will explode, basically. Okay? So let us write it this way so that it's clearer. I will take this as the limit when epsilon goes to 0 of the same thing. By the way, I can just kill the factor 2 here and here. Okay. And I can put that like xi minus 1. And here, let me take first that bound. So it's epsilon to the power 2, 1 minus xi, minus d max. So clearly, when xi is bigger than 1, we have a problem. So let's look at the two limits. If xi is smaller than 1, well, n is equal to pi b, and it's regular here, so I don't care about the first term. I can put 1 minus xi, and then d max to 1 minus xi. And so it's a number because xi is a finite number, pi, b, the concentration as well, and the distance I'm considering as well. So this is a finite number. However, if xi is bigger than 1, then this number is mostly, let me take the equivalent, which is dominated by that behavior. We neglect the constant part, so it's dominated by that behavior. So it's pi b c naught tilde xi minus 1, and then you are left with 1 over xi to the power 2 xi minus 1. That's the dominant behavior as epsilon goes to 0. Okay? And so this is going to infinity. So it means the number of counter ions approaching the cylinder within this box, no matter the size d max of the box, by the way, is going to infinity. So of course, this is not physical, but it means that there is a phase transition or a condensation. All the ions are coming suddenly and will basically accumulate on the line. Plenty of remarks could be made of course, the cylinder is not an infinitely long line with zero thickness. It has a molecular thickness. So you could regularize all the electrostatic problem by taking into account a finite size of the cylinder or the axis of the DNA. And therefore, this number will not be infinite anymore. It will be only very large, which is equivalent practically. It means that all the ions are coming. Okay, so infinity is really due to the fact that we are considering a line, but the argument is more to say that there is a particular value of Xi beyond which most of the ions will accumulate. And secondly, the fact that the number is infinite suggests that there is a phase transition and that something else occurs. So in fact, the ions are not free ions anymore, but they will really transform into a liquid layer of ions around the DNA, and you will change the problem. Now you have a molecule which is dressed by a kind of layer, a lubrication layer, if you want, of ions touching. It can be even a crystal-like layer of ions on the DNA. So it's a kind of renormalized object. Okay. Then, and this was question number 5. Let me just not lose everyone here. All right. And so now we are thinking a bit more about what happens when Xi is bigger than 1. Xi is bigger than 1. There is condensation, so there is a phase transition. And according to you, when this will stop? When will this stop? So you have your naked DNA line. Ions are accumulating because Xi is bigger than 1, okay? Meaning that if you want, the spacing between the charges on DNA is very small compared to the typical electrostatic versus temperature length. And therefore, it's a very charged object, this DNA. So it attracts a lot of ions, they condensate, but at some point it should stop this condensation. So according to you, when will this stop? You know, when the ions are coming to DNA, what they are doing as a layer, they are changing the effective size of DNA. So in a sense, they are reducing the effective Xi, okay? They are spacing again the native charges on the DNA. So there is a screening mechanism going on here. So what is the limiting value for Xi? Well, it will be 1. So as soon as Xi is bigger than 1, you have condensation. So you're attracting a lot of ions that start to decorate your chain. And it will continue as long as Xi is bigger than 1. If at some point, by accumulating those charges, you are effectively reducing the charge on DNA, meaning you are spacing more and more the effective charges, so B, you are increasing B, then you will reduce Xi, and at some point, the condensation mechanism will stop when Xi is effectively close to 1. Stop when effective Xi reaches 1. So we say that basically Xi is in fact 1 plus delta Xi, where delta Xi is positive. And Xi will be effectively reduced by the condensation mechanisms so that you end up to that value. So I can rewrite the following, saying that delta Xi is Xi minus 1, and I can even normalize it to have a relative variation, and this is 1 minus 1 Xi. Okay, so this will be the reduction operating thanks to the condensation mechanism. It's the reduction of Xi. Let me just come back to the physical meaning of Xi. Xi is, we said, the Jerome length divided by B. So mathematically, or physically rather, it's 4 pi epsilon kBt for Jerome divided by B. And here I can decompose it in 2 charges, just to discuss a bit, which have different meanings. The first one is the charge, you remember the calculation we made so far, is the charge that appears in the potential itself here. Thanks to the Gauss theorem, we ended up with the formula of the potential created by the polymer line. So this E is a chain E. It's the E belonging to the chain. Whereas the second one is coming from the counter ions. As you can see it from the interaction energy. Okay, so this is coming from the counter ion. It's the minus E. So I can always say that since there is this condensation mechanism on DNA, in fact, I'm reducing effectively psi by a certain amount. This is equivalent to reducing the native charge of the DNA. So in a sense, what I'm doing is that when I write delta xi over psi, it's in fact delta E chain over E chain, right? So this formula is important. This is the relative fraction of screened charges of DNA by condensation. It's a positive number. So it means over all the charges that you have on DNA, since there is a massive condensation of ions on it, I'm reducing the charge on DNA, and the amount of reducing is delta E over E. It's 1 minus 1 over psi. So it's 0 when psi equals 1, strictly, but as psi becomes bigger than 1 is non-zero. All right, so I could also have introduced another quantity, which is the fraction, which is the one that you are interested in if you do biophysics, for instance, the fraction of remaining charges on DNA. After condensation. Well, this is 1 minus what we already found. So it's 1 over psi. So, and remember, we are in a situation where psi is bigger than 1. So if psi is very big compared to 1, then at the end you have a few charges left on DNA on a relative fashion. You have a lot of charges that have been screened by the fact that you have plenty of counter ions coming on DNA. Is it clear? Do you have any questions on that? Any comment? No? Okay, so let us continue then. Then we are asking another question. What if you have polyvalent, multivalent counter ions, meaning that instead of having minus E as the charge of the counter ions, it becomes minus Z psi with Z, which is bigger than 1. So you still have DNA, which is a line made of positive charges E. But now the solution, for instance, you have calcium inside your cell. So you have minus 2. Oh, sorry, it's not plus 2. So this is, I would do real DNA, and this is plus 2 for calcium here. And so those are divalent ions. And so how is everything changed? Well, remember what we wrote here. The counter ion charge is modified now by a Z in front, which means that you have Xi that becomes Xi that becomes Z Xi. And so the remaining fraction of DNA after condensation is becoming 1 over Z psi. Remaining fraction. So therefore, the larger psi, the larger the condensation mechanism first, but also if the counter ions themselves are multiply charged, well, you increase a lot the effect. So you reduce, again, even more the remaining charge on DNA. All right? So let us now put numbers, realistic for biology. So we go to DNA, and DNA, well, the typical distance between charges on DNA is something like that, okay? So it's kind of monomeric size, so it's very charged if you want. This is native. This is, if you look at your DNA, it's decorated with phosphate groups that bear a negative charge, and this is the distance between those. And we know that we work at temperature, which is the body temperature typically. So if you put orders of magnitude, try, Xi again is provided by this formula. So can you estimate it? So the Jerome length again is 4 pi epsilon kbt, and then you have B. So what is the typical value for that? Remember, in water, epsilon is 80 times the vacuum value, typically. So for DNA, can you provide me the value of Xi quickly by doing an estimate? Anyone? So E is typically 10 minus 19 in Coulomb, okay, in SI units, and epsilon naught is 10 minus 10 minus 11, sorry, and KB is 10 to the 23, to the minus 23. Okay, so we get something like a few units, 4. So Xi for DNA in realistic condition is much more, is bigger than 1. So you have condensation, and so the remaining fraction of charge is 1/4, which is 25%. Meaning over 4 phosphate groups on DNA, 3 are useless at the end because counter-ions came on it, and so you are left with only 1/4 that is still active on average, of course. So in fact, it's not because you know the composition of your monomers, of your biologically relevant polymers like DNA, that you know exactly the forces or the charges in a realistic situation. In fact, you have counter-ions around, you have this very important and fundamental condensation mechanism that says that in fact is much less charge that you would expect. And so it has dramatic implications because if you reduce by 4 the charges, it means you will reduce the rigidity of the object, DNA. You will change the interaction between monomers themselves. And so all the process of coiling, uncoiling of DNA, cutting and gluing and copy pasting DNA, well, this will be affected by this number. So you see, this mechanism is actually very important. Okay, so that's the main idea of the paper by Manning, and you can have a look at it to make your own understanding of things. Now I would like to go one step further. If we do so, it means that there is plenty of counter-ions that are useless as well in the cell. If you have a realistic cell with plenty of polymeric objects that are all charged, well, you have this condensation mechanism probably, and then at the end, the remaining fraction of ions in the solution is modified. And so it's important because the calcium ions, for instance, are ions that will allow the cell to communicate with the outside. You will have some osmotic pressure, for instance, that will help you transitioning from inside to outside or vice versa. And so this will have a dramatic effect beyond simple DNA physics, okay? Also for other processes in the cell. So we need to reevaluate the counter-ion properties after the condensation mechanism in particular. And this is what we would like to do. But first, to do so, I would like to do a quick reminder. So I'm sure you all know the Debye-Huckel framework for having plenty of ions in a solvent and with temperature in a canonical ensemble. But I will just briefly recall it to you so that all the students are on the same page, okay? So this is just a reminder before we use that framework to go one step further in the description of the ions. All right, any questions so far?
No, thank you.
Okay, perfect. So let us go on. So the Debye-Huckel, the framework is the following. So we consider a solution. In these solutions, you have plenty of ions, and basically we will assume that they have several types. So I is the species considered, for instance, calcium. Another one, species is characterized by a certain valency, 1 charge, 2 charges, 3 charges, and etc. And a certain concentration. How many do you put into this volume? So it's a native concentration. That's why I put a note on it. Okay, so I have this bag full of ions, and I would like to calculate the properties under the fact that it is at a given temperature with a reservoir in the canonical ensemble. Okay. All right. So first of all, we want this big source to be electron neutral. So the total number of charges, or the concentrations here, because the volume is fixed, multiplied by the charges of species I, summed over all the species, well, should be equal to 0. This is stating the constraint that you don't want any charge on the global level. And so this is equivalent, if I remove that guy, of saying that this quantity should be equal to 0. Okay? So now we would like to reproduce the classical description by Poisson-Boltzmann and the Debye-Huckel successively. So the idea is to take one test ion, and let's assume it's from one species, a particular species J, and at a certain distance R from it, it will create a certain potential phi R. And now I will put at that position an ion of any type, let's say another index I, that will fill this potential and that will interact with it, okay? So the question is, what is the energy between the two? And I can call this U of J over I, and it is simply, well, the charge of the ion here at distance R multiplied by the potential created by the ion J. So this is the interaction energy felt at this point. All right. Now I know the energy, and I remind you that we are dealing with thermal fluctuations and the presence of an ensemble at temperature T here. So the concentration of the ions is in fact modified with respect to the native concentration, due to the fact that now you have some potential of interactions here in particular. Now you have a Boltzmann factor that says that the concentration is modified. It's not uniform anymore around the test ion, of course. This is a mean field approach here. And now you have the main concentration in prefactor and the correction Boltzmann factor. All right, so that's the concentration of species I. And from that concentration, we can calculate what is the density now. So the total density of charges will be the sum over all the species of the concentration times the associated charge of each species. Okay, so it's the sum over i's of, and then So the main message that we have here is that the density of charges is connected to the potential, and it's connected to the potential by a Boltzmann law. Right, so it's the first connection between the two main fields of electrostatics here. So we need another equation, and according to you, what will be this other equation?
It's the Poisson equation.
Yes. Yes, so now we took care about KT in a sense by Boltzmann. We would like now to consider the electrostatic problem itself, and so we have the Maxwell equation here, in particular the Maxwell-Gauss equation. So remember that this is the connection between the field and the density of charges. And in electrostatics, you also have the property that this derives from the potential, electrostatic potential. All right, so the gradient the divergence of a gradient is a Laplacian, so you end up with the Laplacian of phi, and the minus sign makes everything on the same side of the equation. So this is the famous, as you said, Poisson equation. Connecting once again those two objects. And so now the problem is closed, and I could combine the two. So delta phi plus sum over the species, and remember it was all times the exponential of minus z I e phi over kbt. And now I've closed the problem because I have an equation purely on phi. And then if I solve for phi, I can just plug it here and get the density, or here, it's the same, okay? So I'm now concentrating on that equation that we call the Poisson-Boltzmann equation. All right, so next part is this equation. You can solve it numerically. You have particular cases where you can still solve it analytically despite the non-linearities. However, in general, it's difficult to solve, and analytically, I mean, and to understand the main behavior of it, we can go to the Debye-Huckel framework, which is the dilute situation. So if you have a dilute situation, or limit, you could say that basically the charges are typically quite separated. Therefore, the typical potential phi here is pretty small compared to thermal energy, in a sense. And so you might be allowed to expand in a Taylor fashion this exponential. I only keep the first term. So the zeroth order term is very useless because it provides you the problem without any thermal effect, and you don't want that because you want to be considering the fluctuation. So let's take the order one, and the order one is the following. So I expand the exponential at order one in the argument and neglect all the remaining terms, okay? I can simplify that further. Here you recognize the sum over I of Zi Ci naught. And so this is, if you remember, the electron neutrality constraint. So the first part here will be 0. So I'm left with delta phi is equal to sum over I and I can even group those guys together and call that, you see you have a Laplacian operator, which is a second derivative with respect to distance typically. So this must be the inverse of a distance squared that I call the Debye length. So epsilon kbt, then you have E squared, and then you have something we call the ionic force, where the ionic force is simply defined as the sum over I of concentration times the squared of the valency. So the larger the concentration of charges, or the larger their charge power due to the valency here, the smaller lambda d. And we will interpret that in a minute, but I'm sure you're all familiar with this, okay? So you have this equation that we can rewrite here, and remember that phi is in fact a function of the distance only. So the Laplacian here will be in spherical coordinates, it will be simply, so with full derivatives here. Okay, that will be the operator. So now I can transform the previous equation into of phi prime, with prime being d over dr, just a notation, equal to, what do we have? We have phi over lambda d squared. Okay, and I can even introduce dimensionless notations such that I don't have any more length scales in the problem. So this is capital R, it's a dimensionless variable, and phi of R will be transformed into capital phi of capital R, a dimensionless function. So this allows you to say that, well, in fact, you have a purely mathematical problem in the form. And now the prime is the derivative with respect to capital R, it's only variable. Okay, so no more length scale. It's a scale-free problem here. Okay. So in the absence of the thermal effects here, so if I neglect, if I say temperature is infinite, so you don't have any more exponential factor here, then you are left with the pure Poisson equation that becomes a Laplace equation. So it's delta phi equals 0. And if you solve that, you recover the electrostatic potential, which is in 1 over R typically. So it seems reasonable to think about the following change of variable and to say, well, let me look at a solution that keeps this kind of symmetry. I'm looking for something that will be 1 over R typically, but with a correction that I don't know yet. And writing things this way, I don't lose any generality. All the unknown part is put into this new function, okay? But I keep the form because I'm guided by the fact that in absence of any thermal effect here, I recover the Coulombian potential, okay? So let me just do that change of variables here. So I have, if I use this equation and this change of variable, I get 1 over R squared. The derivative will be U prime R minus U over R squared. And this should be derived again. And then I have U over R. So here I can really simplify at least the denominator once. So let me take this object. Okay. And I can write it further. Let me take another blackboard. So it's 1 over R times, let me simplify the first thing. You have the R square that vanishes. So you have U prime R minus U, but derived once more. So it's u second r plus u prime for that term minus u prime, which should be equal to simply u. Okay. So I end up with a simple equation, which means I was correctly guessing the good shape for the change of variables. Okay. This is an ordinary differential equation, which is linear with constant coefficients. We know the solutions of that. It's a combination of exponentials, right? All right, so now I can recall that phi was u over r, meaning a over r plus b over r exponential minus r. That's the potential in dimensionless units, and I can now put back real units. So it's the, so let me just change notation, or it will be another constant. I absorb the definitions of capital R and small r over lambda d, C1 plus C2 and C2 I will simply call it C because this is the one that matters after. Okay. Anyway, so I'm ending up with this general formula, and now I need to specify the two constants, C1 and C. So we need boundary conditions. The boundary conditions are of two kinds. I need the long range or the far field boundary condition, and I need a near field boundary condition. Okay. So what do you think about the large field boundary condition? It's pretty obvious.
It vanishes?
Yes, at least we don't allow for an infinite potential far away. Okay. So I agree with your statement as a consequence, meaning that basically we will kill C1. Because when R goes to infinity, we don't want an infinite potential. This is not allowed by physics, okay? All right, so we end up with a vanishing potential far away. Okay, problem, when R goes to 0, well, this is a very gentle function. It would tend to 1. And this will diverge. And we are actually coming back to a very fundamental problem of electrostatics. It's the same for gravity as well. The fact that if you have point-like particles, the potential at that point is infinite. So we should regularize that view. And what is the argument? What is the argument? And I think it's question number 7 now. This is question number 7. And so what is the argument in the near field? We say that when we have really a singular point in electrostatics, the potential at this point, the Coulombian potential, or any potential as we can see here now, will diverge. This is due to the fact that we are modeling charges by points. So how can we regularize that problem?
We say that it has.
Yep.
We say that it has a certain size.
Yes.
And so the potential should be the same as a Coulomb charge with the same size.
Exactly. So the problem comes from the singularity in the description, meaning that we are creating point-like object with a finite charge. So let us regularize this and remember that in fact the charges cannot be points, but they have a certain extent. And so we end up with recalling the fact that in fact at the end you have charges with a certain size A, which is very small. And this is your near field approach. So let us take one charge like this, and calculate the field at the border of that charge. And this will be my inner boundary condition for the problem I was solving in this domain here, okay, far away. I was solving phi at a certain distance r, assuming that it was a point-like object. But now we would like to know the boundary condition here at a finite distance. So basically, this amounts to evaluating the potential or the electric field, its equivalent, at the boundary of an ion of a finite size A. All right, so let's apply Gauss theorem again. Due to the symmetries, the potential is radial, the electric field is radial at the boundary here, and you have 4 pi a squared, which is the surface of that ion. And this is the Gauss theorem, so it should be equal to the charge of that ion. And remember, in this view of a test ion that was drawn, where was it? Here. The center was the test ion of species J. So we know the charge of that guy. So here it's a J-like object. So the charge is Zj times E. And thanks to the Gauss theorem, we have an epsilon here as well, meaning that I know the potential at point A, which is the famous Coulombian potential at a distance A with a dependency in A squared. Yeah, that's the potential. So now, if I know that guy apart from a prefactor, I can calculate E of R and make sure that when R goes to A, I recover that boundary condition. So it's the inner boundary condition of the problem. So where is phi? Phi is here. Again, phi is C over R exponential minus R over lambda d. So phi prime is equal to minus C over R squared minus R over lambda d, and minus C over R lambda d minus R over lambda d. And the electric field is minus phi prime, so it's C over R exponential minus R lambda d, and I can put R squared if I want. So 1 plus R over lambda d. Okay, that's the electric field in the whole medium, and in particular, this tends to. So this is, let me call this in, and this is out. Okay. So this is C over A squared and so the boundary condition means that E out should be equal to E in when you evaluate those at the boundary of the ion. So this provides the connection we wanted. We have Zj E over 4 pi A squared epsilon, which is equal to C over A squared. And you immediately see that the regularization operates because you killed the two divergences. Remember, those guys were going to infinity, but similarly. And this is going to 1 as A goes to 0. And this is going to 0 as A goes to 0. Okay, so basically we found C. C is equal to C is equal to, this is 1, so it's simply the Coulombian prefactor. And C was, where was it? C was the constant in the potential. So I can now rewrite the full solution. Phi of R is equal to Zj, the unit charge. And then you have R and the exponential. So we found the potential, electrostatic potential created by the test ion at the center of the universe here at a certain distance r from it. Comments are the following. It's in fact the Coulombian potential, as if this ion was alone in the universe. But you have a screening factor due to the counter ions. Why the counter ions? Because lambda d appears. Remember that lambda d was, or lambda d squared was kBt epsilon over E squared times the ionic force. And so the ionic force is the sum over the concentrations of all counter ions and their valencies squared. So the Debye length, as we all remember now, is the distance over which the potential of Coulomb is screened. So you have a charge in the universe, it radiates its potential very long range, 1 over r, as usual. But the fact that you have plenty of other counter ions around will create a cloud of ions, and viewed from far away, it will screen the potential. You won't see any more potential beyond a certain distance. That depends on the concentration of ions. Okay, so you kill the electrostatic aspect of the problem. This is also reminiscent of what we call a Yukawa potential that you recover in high energy physics, for instance. So in the standard model or in classical quantum field theory, this is associated with the fact that when you have a certain boson that is mediating the interaction, if this boson has a certain mass, which is non-zero, then you will have a short-range potential of interaction. You can think about the reverse. If your boson has no mass, like the photon, then it means that you have a very long-range interaction. This is the Coulombian interaction. As soon as you put some mass to the mediating boson, then the interaction will be short-range. So this is the Yukawa potential that is found in high-energy physics, but it has exactly the same shape here for soft matter physics. Okay, so 1 over r behavior, or let's say a rational behavior, multiplied by a screening exponential. Okay, so that's what we need for the following. I'm sure you are all familiar with that, but since you all come from different backgrounds, I wanted to just recall that depending on when you learned such a feature. So we are now able, in some approximations, of course, a dilute system, no temporal variation, so it's very statics, equilibrium, and so on. We are able to describe the effective interaction in presence of plenty of ions around. And this will be useful for DNA in a cell. That's what we want to do now. Do you have any question on that little detour? No? Okay, so remember, the first part, we were taking DNA as a solitary object with equally spaced charges on it. And we were considering one counter ion first and calculated the interaction between the two without any effect of the other counter ions around. Okay, so it was really an individual problem in that sense. And so we calculate and we demonstrated the fact that, well, this counter ion is attracted to the axis. Okay, and so we calculated the number of independent counter ions accumulating on the backbone of DNA, and thus the condensation effect, and thus the renormalization of the effective charge. But we didn't, or we haven't taken into account the fact that those free ions will also screen the potential, will decorate the chain itself. And this is what we would like to do now to terminate. And so we now want to put back into the focus the role of counter ions, their concentration, their osmotic pressure, and really study them as a gas of counter ions, and look at the concentration that is remaining after all that condensation business. So I hope the program is clear. So now we come back to the situation above, and we really consider a cell. Let's say, assume it's a cell, very simple object like that. Inside you have plenty of DNA-like molecules, okay? You have a certain number n macromolecules. This is the number of macromolecules. Each macromolecule, this one, for instance, well, it has charges, again, remember, spaced by B. And you can say that it has between 1, 2, 3, and n charges, okay? So I have n, small n charges on, so this is the number, and small n is the number of charges per macromolecule, or per chain, it's the same. All right, and we put all that into a cell of a certain volume V at a certain temperature T. So number is fixed, volume is fixed, temperature is fixed. We are in a canonical ensemble, and we add an ingredient of importance. We have charges everywhere. So we have counter ions everywhere to ensure electron neutrality in particular. And those counter ions, well, they will fill themselves, they will fill the chains, they will condensate on the chain. We have all these effects. And at the end, we would like to know, well, do they all really matter, or some of them are really doing the condensation or some screening effect? So how many of those are really important in the cell? The other one being doing another job in a sense. So if now I want to take my cell and open a little pore and do some electric transport between in and out of the cell, I don't know, to communicate, for instance, in a synaptical way, or to exchange some information with just the neighboring, or to admit some object inside. For instance, a protein wants to enter the cell. Well, I will use the osmotic pressure to make it enter, to push it inside, whatever. Well, this will be very important to know the actual number of ions contributing to the osmotic pressure. So you see, we start to elaborate now a bit more. Of course, the complexity is really reduced. We don't consider the fact that it's an out of equilibrium system, a real cell. We are all dealing with equilibrium stat phase. So first, it's a big step. Secondly, we are neglecting plenty of other objects inside the cell, as you can imagine. But still, we are trying to give some arguments to understand a bit the fact that the counter ions are in fact not as numerous as what we would thought initially, which will change the communication aspects of the cell. All right, and first, to start with, we will assume that psi is smaller than 1, meaning that we have no condensation. This is either true because the charges on the DNA are very spaced, first possibility, or they were not spaced at all, but there was already a condensation mechanism, and now we have redrawn the drawing after the condensation mechanism. So we are back to a situation where psi is smaller or equal to 1, okay? So this is our starting point. And we would like to evaluate the osmotic pressure of that system. All right, so anything else in the énoncé that I have missed, perhaps? No. So we would like to calculate now the potential created at a certain distance of the polymer chain, the DNA chain. So let us take one chain again with a linear charge E over B. And now we consider a certain point D. This is again the z-axis, and we would like to know what is the potential, but now including the contribution of counter ions exerted on that point by all the chains. So we will basically sum the contributions of elements dz on that point, okay? And this is z, and this actual distance is d squared plus z squared by Pythagora, okay? So the total potential that I feel here will be the contribution of all those small segments. So I will integrate, basically, the potential that I can call phi here, okay? So phi at a certain distance d will be the summation of d phi, where d phi, or psi, sorry, d psi is the potential created by this little segment at a distance d and taking into account the counter ions. So it's really something like that. It's a Colombian plus counter ion potential, but for a small segment. So d phi is, remember, you have the Colombian factor, so you need to know the charge that is created and the distance. So the charge is, well, it's dz over b times e. So I multiply the linear fraction times the little increment of space to have the effective charge, divided by 4 pi epsilon, and then the distance, and the distance is square root of d squared plus z squared. Okay, and then I have the screening exponential factor minus what? Minus the distance, so this guy over lambda t. Any question on that? It's clear for everyone? I assume it's the case then. Okay, so the integral can be rewritten in the following way. So you have the integral over from minus infinity to plus infinity, dz. You have this constant that I will soon move outside. And then you have the dependencies here. So I can just put lambda d at all denominators and multiply this by lambda d. I put the lambda d here, for instance. Okay, and so I can introduce a change of variables. For instance, u will be equal to my integration variable in units of lambda d. And I will also define s, which is the same, but it's the parameter of that integral. So the distance I'm considering in the by length units. And so by this change of variable, I'm left with 4 pi b epsilon du over r, I don't specify it further, minus square root of what? Of u squared plus s squared divided by, well, in fact, let me add the bounds. Because this function is obviously a function that is even, pair en français, and thus there is a factor 2. So it's also true that I can have this. So it's more compact. So in fact, as we can see, since u is integrated everywhere, it's only a function of s. Okay, so let me just put that on the next slide so that we can work. Is there an epsilon? And that's all, yes. All right, that's the object I would like to estimate. There is also an obvious change of variables. I can introduce it here. Let me call that t squared. So it seems then this guy will be exponential minus, what do we have? We have minus t over t, and also u squared is equal to t squared minus s squared. So u is right, and thus du is equal to with t, right? So I'm left with dt t and square root of t squared minus s squared here. Okay. So in particular, I can kill these guys. All right. So, and this is t is going from s squared, so from s, sorry, to infinity. So s infinity. Let me just summarize here. Okay, so I want to evaluate that object. So this is a general formula. And I would like to consider the expression of that when S, remember the expression of S here, is very small, meaning I'm looking at a near field region. I want to really look at the effect near the backbone of DNA. So question, what happens when S goes to 0? So when S goes to 0, let me write an equivalent of that. Here it's epsilon over, sorry, it's E over 2 pi b epsilon. I will keep the bound for now. It plays a role in the equivalent. And dt, and here typically it will behave like when S goes to 0, like 1 over t. And basically the main problem is where? The main problem is as S goes to 0 is this bound. Because you are integrating essentially 1 over t, because near 0, this is 1. It's a very gentle function. So the dramatic part is the denominator that is linear in t. So the integral of that is a log, the primitive, and a log of 0 explodes. It's minus infinity. So this is really dominated by the bound that is here. So it's essentially behaving in the limit where S goes to 0 by log of minus log of S. Okay. And so we recover, in fact, this is not a surprise, we recover what we found with the first calculation. We recover the fact that the potential is logarithmic in distance. Remember that S is the ratio between distance and the bilength. But now what we have done is to specify the constant. Now we know that psi is made of 2 terms. I can separate them like that if I want. If I put everything in unit of 1 meter, for instance. So I have a potential. And this is the one we had before. In fact, we already got this one. Let me just remind you where we were. At the very beginning, we calculated the field created by the line here. And what we found is this guy. So we had a first term that was a logarithm of the distance plus a constant that we never specified, because at the end, the constant was only an additional energy that was the same for everyone. And so it was put into a renormalization of the prefactor in the Boltzmann law, remember. So now we've specified that in a specific case where they are counter ions. It's here, okay? And so I can formally express things saying that this is a chain contribution. This is the one we did at question number 1, the first part. And we call that psi1. And there is another counter-ion contribution that we call psi2 as a notation, all right? Any question so far? Not? Okay, so what we've done is to calculate the potential created at a certain distance of one polymer chain, okay, under plenty of assumption, rigidity, equilibrium, no dynamics here, and a dilute assembly of polymer chains. We don't consider interactions between two polymer chains, okay, they are sufficiently far away. Now we would like to use that to calculate the properties of the cloud of counter-ions, the yellow part in this figure. So this is what we will do now. Let me start now from the beginning. So I will keep only psi2. So psi2 up. So this is the next question, I think, question 3. So what we just found is that the potential is, and I guess it was a plus, right? Let me just make sure I don't lose any sign. Yes. All right, sorry for that. So I have the counter-ion potential, and I already studied the chain potential. They are additive, so I can look at the two contributions separately. So let us look at only the counter-ions contribution, because this is the one I don't have yet, and I would like to study a bit more. So now, and this is the argument of Manning. Manning introduces the work needed to bring the counter-ions from their equilibrium distribution to the situation in presence of the polymer chain. Okay, so what it does, basically, you already did that calculation for gravity. For instance, if you want to calculate what is the internal energy of some planet or some star, what you do is basically you bring material from infinity and you calculate the work to do so. So it's the gravitational work, okay, and then you sum that for any corona around the star, and by summing all those contributions, you end up with the internal potential gravity energy, if you want. So you do exactly the same here. You take a cell with neutral DNA chain. You have some counter-ions here, and then with a certain homogeneous distribution, and then you branch the charge continuously, mathematically, if you want, on the DNA. By doing so, you are attracting the counter-ions towards the chain, and so you can calculate the work, and this will, in fact, be the energy of the counter-ions after the operation. Okay. So this is what Manning does in the paper I've sent you. So the work is defined as, for each charge, so it's multiplied by the number of charges, is the integral of the potential, psi2, but with, so let me put notations here. So for the integration part, you have E prime. This is the variable. I put a small prime here. This is the charge on DNA, and I will branch it from 0 to its final value E, and I will calculate the work. So the product of potential and charge, it's an energy. I calculate the work when I do so. Okay, when I branch the charge on DNA, and so here psi2 is not a function of E but E prime. It's the integration variable, and I do that for one polymer chain, but for every charge on DNA. So it's N 0 E, E prime 2 pi epsilon B and log lambda D. And an important aspect here is that this is E prime is really the chain charge, whereas in lambda d, remember lambda d is kBt epsilon over E squared times the ionic force and with the square root, but this is the charge of the counter ions. So it's not the same. We don't consider this E. It's not an E prime. So it's not integrated, this one. So the log lambda d, it's purely counter ionic, it goes outside. And then integrating E prime between 0 and E. So there's a d E prime missing here. Sorry about that. It's E squared over 2. So you end up with the work, meaning the internal energy of the counter ionic cloud, which is n E squared over 4 pi epsilon b times the log of the Debye length. That's the work. So we have the work for one chain. Now, what is the total energy per unit volume in the cell? So U is the total energy. It's N times W. Okay, so 1 for each polymer chain, 1 for each DNA chain. And per unit volume, I'll just divide by the volume. So the internal energy of the counter ionic cloud per unit volume is NV, what we found before. So N 4 pi epsilon B, and then log lambda d. All right. And we can work this a bit more by recognizing several things. First of all, N number of chains, N number of charges per chain, and V the volume. This is the concentration, the total concentration of DNA charges in the cell. And by electron neutrality, this is also the total concentration of counter ions, by the way. We have to have this correlation. Okay, first thing. And second thing, here we recognize something like the Bjerrum length. So if I multiply by kBt and divide by kBt, and I incorporate this kBt as well here, well, I have, I recognize Xi, which is Bjerrum length divided by 1 over B. So there is a Xi and there is a KT. So I can rewrite everything. The energy per unit volume, eternal energy per unit volume, sorry for my notation, is the total concentration of charges of DNA, of all the DNA chains. It's Xi, the central Manning dimensionless number. It's homogeneous to kBt because it should be an energy at the end. It's an energy per unit volume, so energy per unit volume. And then you have a logarithmic, due to the geometry, contribution of the counter ions. And I think we are done. This is the internal energy per unit volume. Any comment on that? Is it clear? Okay, I take that as a yes. And so we can go on. Now that we have the total energy, we can calculate, I mean, it's internal energy. We have the possibility to derive pressure and all the thermodynamical quantities we want. So it's, I guess it's question number 4. No, 5, sorry. Yes. So we want to calculate the osmotic pressure, but first let us remember what is the osmotic pressure of a free gas of counter ions. So you have ions everywhere in a certain volume. We assume they are dilute. What is the osmotic pressure? Does anyone remembers that? Call that the bare osmotic pressure. So I have C dot is equal to the concentration of DNA charges, but by electron neutrality is also the concentration of counter ions. So what is the osmotic pressure if I have a certain concentration of ions? Forget the polymer chains, forget everything. It's a dilute reference here. Any memory about that? Anyone?
Isn't it the sum of I of the concentrations of counter ions times KBT?
Yes, it is. So here now they all contribute like that. So it's KBT times C dot, right? Pressure is equal to KBT times number divided by volume. Well, it's an ideal gas formula. It's called, in fact, the Van 't Hoff formula for osmotic pressure. And what do we have here? We have, in fact, that basically the pressure, the osmotic pressure, is of anthropic origin, and is simply proportional to the number of objects. So the more salt or calcium you add, the more osmotic pressure you have. So if your cell is full of calcium and the outside is purely neutral, it might be that you will have a strong pressure to homogenize that, and basically water from the outside will enter the cell to dilute calcium. Okay? And of course, if you now have a dense assembly of charges, this law doesn't work. You have to go beyond the ideal description, the ideal gas, and so you will have like a van der Waals gas, if you want. So we start to have interactions, excluded volume. So that's the next correction. And in fact, you can put any correction you want or any potential you want. But this is the simplest description to get a feeling. So this is the reference. And so here now we are saying that, well, we are not in that case because we have some polymer chains in the cell. Remember the drawing. Here, we are not dealing only with yellow stuff, but we have those chains, they create a potential, so they modify the concentration. There is a very difficult problem apparently here. And so what is the real osmotic pressure? Well, we can simply say that it's the sum of two objects. It's the reference case plus a correction. I've written nothing here. But what I'm doing now is to say, well, and this is not an unknown object, is simply the derivative, or with a minus, because the pressure and volume are related with a minus, of the internal energy with respect to volume, everything else being constant. So N temperature, okay? Agreed? So P0 is an ideal gas of counter ions that are completely free to be everywhere. But as soon as I put polymer chains, it will change the pressure. And so I use U, which is the work or the internal energy of counter ions where they are in presence of the DNA chain. So it's minus the derivative with respect to volume of U, which is N times psi times KBT times log of lambda d. I've multiplied by V, so you don't have C dot anymore, but only the numbers. And all this will jump out because there is no volume in these guys. So it's minus N psi KBT times the derivative with respect to volume of log lambda d. And remember, this should be evaluated at N and T fixed. And here there is no more N and N, so it's at T fixed because I put them in front. Okay? All right, and so now we would like to know the variation of the log of the Debye length with volume. And we have to remember that the Debye length, at least its square is provided by kBt epsilon E squared, and then you have the ionic force. But the ionic force is what? In my case, so in general, it's the sum over all species of concentration times valency squared. That's the definition we found out. But here we have only one type of counterion, and their charge is minus E. So in our specific case, it's C dot, the concentration of counterions, times E squared. And in fact, excuse me, there is still N and N, I realize, here. Okay, like here, and like here. Okay, so it seems that this is proportional to 1 over V. So lambda D squared is proportional to V. So again, my result is that delta pi is minus plenty of things and then the derivative with respect to V of log lambda D. So the derivative with respect to V of log lambda D, and I can put a square here and a 1/2 here if I want. Everything at N and T constant. And the prefactor in this proportionality relation do not matter because it's a log, so they will be simply additive. So I will only consider the fact that this is proportional to volume. And so this immediately provides me a 1 over V. I'm derivating the log of V, so I have 1 over V, and the rest are constants, so they won't play any role. So I end up with minus NN over V 2 kBt psi. And this is a known object, is the total concentration of charges either on DNA or in the entire ionic cloud. So it's minus kBt C dot times psi over 2. Okay, and this is also the reference Van 't Hoff expression. So it's the bare osmotic pressure. Okay, so remember, I was interested not in that, but more generally in the total osmotic pressure pi. So pi is pi naught plus delta pi, so 1 minus psi over 2. And more generally, what is interesting is not this dimensioned relation, but the dimensionless one. I can always introduce a coefficient. I call that the osmotic coefficient, mu, which is pi over pi naught by definition. So let me just check where we are. We are dealing with question number 6 or 7. Okay. Question number 7. Mu is thus equal to 1 minus psi over 2, based on this relation. And it means that, in fact, pi is equal to mu times C dot times kBt. Okay, so when mu is equal to 1, meaning psi equals to 0, we recover the Van 't Hoff law. It's a free gas of counterions. But as soon as mu, or as soon as psi increases, mu decreases, and so we have something which is smaller than 1. And therefore, you can reinterpret that as effective, this is the effective free concentration of ions, or effective concentration of free ions. And so it's smaller than C dot. So initially in your bag, you've put a certain number of counter ions with a certain number of chains, but due to the Debye length and due to the interactions and screening effects, they don't contribute all. Some are already occupied, and only a smaller part of them, mu, a smaller fraction, contributes to the free osmotic pressure. So in a sense, practically, if you now want to communicate between the inside of the cell and the outside, this is mu times C dot that will matter, and not C dot. So you've reduced the osmotic power of your solution. Okay? Okay, final remark I would like to make. What time is it now? Okay, we have still a few minutes. The final remark I would like to make is, now question. What happens in the situation of condensation? So any insight? Does anyone has an idea? So we discussed that at some point. We said, if psi is bigger than 1, then it will be transformed into an effective psi star, which is put back to 1. And at the same time, we say that the concentration will be reduced because you will have condensation of charges on DNA. So the effective concentration on DNA will be different. It will be renormalized. And we said C dot, you have a certain C dot initially, it becomes C dot star, which was 1 over psi. That was our result. In particular, we've taken the example of DNA that was left with only 25% of its charges at the end, okay? Because psi was equal to 4. So this is what happens when psi is bigger than 1. You have a condensation that changes the property. It's a phase transition in a sense. All right, so we could ask the question, then what pi does become? So it becomes a pi star, which is what, well, just replace. We have mu C dot kBT, so where is it? Let's take this expression here. kBT times C dot, so pi is kBT times C dot times 1 minus psi over 2. That was the expression. So pi star is still kBT, C dot star, just by applying the dictionary above, 1 minus psi star. Okay, I'm just replacing all the quantities that have been renormalized. So I end up with kBT, C dot star is 1 over psi, 1 minus 1/2. Well, this is 1/2. So it is kBT over 2 psi. And sorry, I forgot some C dot. This should be still homogeneous to a concentration. My bad. It's only a factor that changes, but it's proportional to the bare concentration. Agreed? So it's also pi naught over 2 psi. So mu, which is pi over pi naught, now is different above 1, is 1 over 2 psi. So as a conclusion, mu is either equal to 1 minus psi over 2 if psi is smaller than 1, and 1 over 2 psi if psi is bigger than 1, so in the condensation regime. So I can summarize those two lines by saying that basically this is my osmotic power or coefficient. It goes between 0 and 1. And this is psi that that passes along the condensation limit. So I have something that decays linearly and that ends up at 1/2. So here I should have 1/2 somewhere when psi is equal to 1. So I should pass linearly to that point. So it's something like that. And then we see that it's a rational power law behavior, 1 over psi. So now it should basically go to 0 smoothly. And sorry, here it's a continuous slope. Okay. So basically, what happens? You start with psi equals 0. Remember, psi is by definition longer Biot length over B is equal to epsilon square 4 pi epsilon kBt divided by 1 over B. So psi equals 0 is either you have a huge thermal energy, or basically you are saying that your DNA, the distance between two charges is going to infinity. So DNA becomes a neutral polymer. So if DNA is a neutral polymer, of course, all the ions present in the solution contribute to the osmotic pressure. They are all free. They don't do anything else. So the osmotic coefficient is 1. If now you branch some charge on DNA, so B starts to be a finite number, part of those ions, they will start to come and decorate the chain, but in a minor fashion. They will basically screen out the interaction between the chain and the rest. So there will be a screening effect. This is a kind of Debye regime, if you want. But at some point, you reach a dramatic situation for the chain itself. You reach psi equals 1, and then you start to have condensation. In that case, ions not only decorate or renormalize the Coulombian interaction, but they start to accumulate massively like a liquid would deposit on a mirror in your bathroom. And suddenly you have plenty of charges that are coming, and so it reduces even further the osmotic power of your cell. And at the end, you can even go to 0 at some point if you have very large values of psi. So it means basically you don't have any more power to communicate or to drive something out or inside, and so on and so forth. All right, I think you got the idea. We stop here. Perhaps there is 1 or 2 questions. Okay, so otherwise, we stop here. I thank you for your attention. I hope it was understandable because you were pretty silent today, I found. Feel free to contact me by email if you have any question, and I can anyway share this video this afternoon in the Dropbox. Okay. So with that, I wish you a very good weekend. Thank you.
Thank you. Bye.
Thank you. Bye.
Bye.